Well, thank you, Jakob, and welcome everyone. Um, so today, what I was the approach I've taken with the paper is I've used a couple of examples out of what's changes and what's a relatively small changes has happened within the Australian mango industry that's had major impact on the way we produce and the way we market our fruit. So to give you a bit of an understanding where I'm coming from, I'll give you a quick overview of the Australian mango industry, where our production time starts up in around 10 degrees latitude around Darwin area, and it finishes around 30 degrees latitude and Gingin in Western Australia. So we're able to produce mangoes from September through to March. So a very long period of production that has numerous peaks within that, where some regions produce a lot more than other regions. Typically, the industry is made up of small and large producing farms. The largest are around the 500 hectare mark. The smallest is probably around the 5 hectare mark. Generally, they're from mixed farms. The industry now is quite dominated production by corporate farms, and they're usually around the 100 to 500 hectare in size. The industry's now got quite a very cohesive industry body that actually represents them at certainly at the policy level when they're engaging government, but also in coordinating strategic planning and strategies for the market access and growth of the industry. It has an underlying support network of research and developments. Traditionally, that was through the state governments and universities. State governments have tended to pull back a bit on their funding, and it's now mostly, a lot of it is industry funded and self-funded research and development. Now, one interesting thing about the Australian mango industry is very, very high cost of labour, probably amongst the highest in the world. And this has a profound impact on what we do and how we grow mangoes, because we have to become very innovative, very efficient at what we're doing. Otherwise, we cannot compete. We can't export and compete with mangoes around the world from low producing cost countries. So we have to be very good at what we're doing. Otherwise, we can't do it. But that's not where the industry was. Traditionally, it was fairly basic sort of production style industry. It was on one variety, and we tried to grow one variety over the whole regions of the country. It was a very poor quality variety in sense for farms production, low yielding, high number of issues with disease and quality, but very, very high consumer acceptance. The consumers loved the variety. The farmers hated it. Very, very intensive labour costs of production, so it made it a very expensive production. And what we found was farmers were just losing money. They're going broke growing this variety. They just could not do it. Found because of those different districts, we end up with lots of different peaks and troughs in the supply chain. So that has a major impact on what happens in the market, particularly in price and supply and demand. And we found with large quantities of poor quality fruit, you're getting price crashes, which was then exacerbating the problems that the farmers were having. So it was really, the industry was really in serious trouble. And this was going back about 20 odd years ago. And wastage was phenomenally high through in the supermarket chain. So there's a real need for change within the industry. So the industry to do this, and again, bearing in mind our constraints that we have, particularly with labour costs and efficiencies, is we really had to take a different approach. We had to go really a market-driven approach. And I'll drop to that point down the bottom there, is we actually, with our traditional research and that, where we're looking at a very much a production-based research, what we found was, yes, there's some great research being doing, but it wasn't helping the industry in the sense it wasn't making them more profitable. They were growing more the same, better, but actually just exacerbating the problem. So we really had to change completely our way of thinking. We did research and development into a market and value chain approach. So to do that, we really needed to understand the markets, and really understand what they were asking for and what their needs. We also then needed to introduce a very high levels of mechanisation to remove the labour factor out of our production. We had to get very, very efficient, again, to reduce costs. We had a big need for new genetics and production systems, again, all in that efficiencies side. We needed to address the most significant quality issues that we're having and understand our post-harvest management systems so we can actually consistently deliver the right product, a good quality product, time and time again into the markets. And to do this, the industry needed to be coordinated and have it in a strategic plan. And that's where the industry associations came in and helped get one focus of what direction they were going. So where we are with the markets, Australia's not a big producer. In any 1 year, it's between 70 to 90,000 tonnes, small scale in global terms. It's still a very heavily domestic focused fresh market that takes the bulk of the fruit, followed by the export market. We're actually quite large, significant exporters in proportion of our crop. It's anything up between 15 and some years even it gets up to 20% of what we're producing. Small processing sector and small amount in the food services. Now the market in Australia is very much dominated by the supermarket chains. We don't have that wet market system you see in Southeast Asia, or very little of it, the independent small. There is some, but it's very, very little and small. But these supermarkets make up 80% of the total volume of sales of fresh fruit. They have the capacity to move big volumes of fruit at the right times, but they need time to plan this. They need at least a lead in of 2 months. And this is important because this is what the industry was not able to do, to give them this time. They didn't have maturity standards, so we're having all sorts of problems with poor quality fruit arriving, particularly early season. Australian mango consumers, we've been growing mangoes in Australia for well over 100 years, so the Australian consumers are well familiar with mangoes. They're quite discerning, unlike sort of European markets, which is a new product. They know what they want. And they're happy to buy big volumes if it's the right type of fruit. But also interesting, what the research is showing us is when the consumer has a bad experience in buying a mango, like an immature mango, they don't come back for another 6 weeks before they purchase. And this is on average before they'll purchase again. And this is a big factor that's suppressing consumption. So the industry telling us this is what the markets are telling the industry. They need a reliability in supply, need efficiencies to keep the costs down to reasonable levels. We need to reduce the losses that they're having in quality. And then they needed some measuring parameters to actually be able to put the maturity, to actually understand the maturity. So they needed some maturity indices that they could measure. They were non-destructive because all the previous ones we had were destructive. They needed a reliable forecasting model so they know when the crop's going to come in, over what time, what the peaks are going to be. And they need to be, and that's backed up by quantifiable maturity standards. So with this presentation, we're looking at those three areas. We're looking at genetics, maturity standards, and production forecasting, and with the quality issues, how the industry's addressed those three issues. So with the genetics, there's been a number of programs over the years. We're based on this one variety. We've gone down the road that most other countries had previously gone down. Introductions of what genetics is out there around the globe. The only real successful one that's come out of that is the Keat. And it's interesting whether Taiwan has gone down with the Irwin. We grew a lot of Irwin in Australia, but we couldn't manage the disease with it. So the industry sort of moved out of that variety. Chart selections, these are ones that have just appeared, through people planting seedlings, and that's where the Kensington Pride originated. And the new one is called the Honey Gold. There's been some research programs that have actually concentrated on planting blocks of seedlings, open pollinated seedlings. And that's where we got the Calypso and R2E2 has come out of that. There were some other programs that looked at selecting within the polyembryonic, because within polyembryonic seedlings, you do get some variation of about 2 to 3%, trying to select within that area, but that was expensive and highly inefficient, so we abandoned that project. But where we really moved in successful is now is a controlled crossing where we actually know the parentage of the progeny. So this is the quick picture of the main varieties, the Kensington Pride. Market loves the blush. You know, to sell a fruit in Australia, it really needs that sort of pink blush with that yellow background is what they're chasing. Now with the mango breeding program, what we've looked at is to produce a series of hybrids that we can actually grow across our range of climatic zones. Not necessarily trying to fit one variety into each zone. Really, this hadn't been done on much scale. I mean, there've been some programs in India that had started. This is really when we were sort of flying blind for a bit at the beginning of the project. And what we didn't have, so there was no heritability data, so we didn't really know, what parent combinations, what genes are highly heritable and which ones aren't. So we had two aims of it. One is to obviously produce the hybrids. The other is also to collect that heritability data, so then we know in future crossing programs we're actually doing it with a lot more precision than what we were. So out of that, we've generated 3 commercial varieties have come out, and they're just in the process of being named at the moment. It's a quick overview of the actual process itself. It's quite labour intensive. We're pretty much looking at pollinating a few flowers, up to no more than 10 flowers per panicle, so you have to strip all the other flowers away. It's all done with the paternal parent then is crossed, capsulated to prevent any cross-contamination of pollen. And yeah, it's successful, but the efficiencies, the best combinations, we were still only getting around sort of 8% success rate with the amount of crosses we did. So it's there's a lot of room to build more efficiencies into this. The selection then, when we're selecting the hybrids, then we really started to use the market information. We had to really rigorously select them against what was really the market wanting. So the varieties had to be much better than was already what was on the market. It had to have the high consumer acceptance, and then progress us forward. This also now moved into a F2 program. We're actually now using that heritability data to do much more specific crosses, and we're actually moving into sort of using molecular markers now for parent identification. So that then gives us now the opportunity to start doing more open pollinated and more efficiencies into the program as well. So the results from the breeding, the genetics improvements, is we now have reliable cropping varieties that we didn't have before. They're now meeting the market expectations. The yields from the farmer's perspective, the Kensington's yielding around 8 tonnes a hectare on average. Many of these, well, all of these new varieties are going over 30 tonnes, and some of them as high as 50 tonnes a hectare. So it's a massive difference in productivity, and that's completely changing the economics of the production systems. So the second section I'll talk about is maturity standards and crop forecasting. This is a big issue that the market was having, is immature fruit, particularly arriving at the beginning of the season, because early high prices, farmers were very encouraged to put fruit onto the market. So then we knew that a 14% dry matter standard, a harvest, was produced a good eating quality fruit from previous research that had been done many years ago. But we were using, currently at that stage, we're using destructive sampling. which is obviously not practical for widespread use, and it's not particularly useful at the market end. So a lot of research was done in actually perfecting the sort of near-infrared technology, which had been around obviously for a while, but actually getting it to reliably determine the fruit dry matter at harvest and at point of receival in the supermarkets. So there's a lot of work done on getting the calibration curves using total soluble solids, dry matter, and seeing where the correlation with them. Also looked at internal colour as well. From that research now, we're very confident we can now measure the fruit using these little gadgets you can see in the photo on the orchards to actually determine when the crop is ready. The supermarkets now allow looking at using it. They now do use these machines on receival. So most of the farms now you'll find these near-infrared, on the larger farms, near-infrared machines. And the industry for the smaller farms actually have a set of them, and they actually share them between the districts. So all farmers have access to this technology now. And it's now become part of the supermarket specifications, and the supermarkets will reject consignments based on the readings they're getting off the machines coming in. So it's been very successful in adoption. Now, how we determined when the maturity, when is the fruit? When do we start looking at fruit? Where there's a number of different systems of actually producing forecasting. Sorry, with the maturity side of it, what we need to do is then go back and say, okay, how do we know when that crop's going to be ready? So that's when we started looking into these forecasting models. So we had to then, so what could we use? And the most obvious one was heat units, because that's measurable. We have long-term data from weather stations, so we can match that up with what. So we did quite a bit of research in actually determining what heat units that were required to mature a variety at certain points of time, and we've used two different stages of starting the measurements. This is what we call asparagus stage, where the flower panicle looks like a spear of asparagus, and then when the Christmas tree, when it's full anthesis, or it's just about to come into anthesis, and it's like a Christmas tree. So the farmers they've got two different stages. They can start measuring the heat units. Very simple calculation with a maximum minimum thermometer. So we get the daily maximum temperature plus the daily minimum temperature divided by 2, get an average, and we then minus 12, and 12 was the figure that was worked out, that at 12 degrees, below 12 degrees, the fruit just doesn't mature. So that was the cutoff point. You can then put that into a model, which all the farmers have based on the long-term meteorological data. And that will give you a estimate of your harvest date. And then as you collect the new data from that season, whether it's warmer or cooler, you will then bring that forward or extend that out. So you actually, as you're getting closer and closer, you're getting more and more accurate. So you've got a long-term position of where it's going to be ready, and then that actually gets calibrated towards as you get the new data for daily data, that brings that model forward. So, and we found this has actually been very accurate. We now do it across large farms. We do it across districts, and we do it across the entire production area in Australia now. So what we do is for the model, is we monitor flowering times across all districts. This is done individual farming properties will then report their flowering, what stage they are at. They enter into the heat unit calculation models, and then that information then is collated by the national industry body and produces a model for the seasonal supply. We also then do, as that flowering progresses, we then start to put in what potential yields based on what crop estimates are. And the supermarkets now can use this as a promotional tool, so they can actually now plan in their promotional programs to move the fruit when the peaks are going to occur. So it's actually getting very accurate now, and this is some data from this is from last season. This grey line, as you can see here, this is what the model, the actual crop forecasting model, was telling us, and this is the actual supply with the coloured, the green and red. So it's getting pretty accurate. There's a little bit of a blip here at the beginning of the season, but yeah, as this model's progressing, it's becoming more and more accurate, and of course the accuracy depends on the amount of data that's put into it. So as a result, now the industry now has some maturity standards that have been set for each variety at harvest. The supermarkets now enforce it at point of receival. So if your product does not meet that standard, it will get rejected. We're seeing very little immature fruit now in the supermarkets. And we've seen now long-term planning of promotionals that are actually meeting the peak supply weeks. And we're seeing consumption increase, and we've seen over the last few seasons, we're seeing price increase. We're seeing higher production, higher consumption, higher prices. So it's having a win-win situation for all industry and supermarkets and consumers. So the third big issue that has impacted on the industry is the quality losses, and we've all those working mangoes, we've all seen it. The fruit that you see on the tree and the fruit that you see on the supermarket floor are totally different products, and there's huge amounts of quality loss in between the fruit tree and supermarkets. We really need to understand what were these quality losses within the chain, where are they happening, and at what extent at each stage is impacting on those losses itself. So there's quite large projects that went back on in the early 1990s, early 2000s. It's actually doing that, really intensively studying load after load, finding out exactly what point in time that these products were losses and damaging was occurring on the fruit. Now, there are a whole numerous set of quality loss issues, but the one we're dealing with in today is the most significant one, which was the sap and latex burn. And that accounted for anything between consignments, anything from 50 to 70% of the actual fruit quality loss. This is excluding disease from the retail chain. So it was obviously the number one that needed addressing. And what also the data is the majority of this damage by far was occurring between harvest and the pack house. Now, the mango with the sap has two specific compounds in the sap. You've got a latex and a sort of protein-based sort of liquid within the saps. Oil-based and a protein-based liquid. The oil content, what we found is it comes out at first, and that's actually what does the damage. And it's highly acidic, and it's actually burning the skin. Now, some varieties are more sensitive skin than others to it. And the problem that the industry is problem doesn't manifest itself at the point of contact and damage of the sap. It comes 2 to 3 days later. Now, what we found was interesting is when we started looking is the oil that's doing nearly all of the damage. The latex comes out later, was virtually doing no damage. What studies have found, it was really between the first 30 seconds of breaking the stem is pretty much you're getting over 90% of the oil, 95% of the oil is coming out at that stage. And then within 2 minutes, you've virtually got 99.9% of the oil content of the sap that's come out. The remaining sap, and they can ooze for anything up to 10, 20 minutes after, that's all the latex protein sort of component of it. And you can see in the bottle on the right here, this is collected a whole heap of oil. This is the whole heap of sap, and this is the oil content sitting on the top of it. And And that's so really what we realize is that management has to be done in that first 32 minutes. Certainly within 30 seconds or 2 minutes is when to manage that burning, because if it's not done, then the damage is already done, and what impact you have down there will be minimal further down the chain. So we gave the issue to some chemists, and they came up with a series of different compounds that we can then neutralize the acid component of the sap. Pretty basic science, just playing around with the pHs. And they've come up with some sort of water-soluble sort of compounds that they can mix. And if you expose the sap, the mango, to these compounds, it virtually neutralizes all that of the pH of the latex, and it stops the burning. Now, initially using our old systems, we're hand harvesting into crates, taking into pack houses. So we looked at incorporating into this pack house, into the pack house system. So this is where the whole process gets very interesting, because this small change in addressing a quality issue completely revolutionized the harvest system of what we now do with mangoes. So we knew that the problem was still occurring in the field, and we're getting a lot of damage between harvest and getting to the pack house. Even though we're using this product in the pack house, yes, that was eliminating some, but it wasn't eliminating all. We had to take this process back right at the point of harvest. So the question was, how could they do that? So then they started looking at, okay, let's try and mechanize this process. And so there's a whole series of different prototypes and different machines came out. Well, we've actually got, if you see these photos, the one in the bottom right-hand corner is probably the best to see. You can see that mist. So the tank under there'll be a tank of water that actually contains the mango compound in it, and it sprays over the fruit. All of these machines have the same principle. They're all spraying water, including the cherry picker here, which has a water tank down the bottom, and that's pumped water to the top, and it's sprayed onto the fruit. So that all the fruit now is sprayed within less than 30 seconds of it being harvested. Usually within a few seconds, within 3 or 4 seconds, it's picked and put straight onto these. These are picked as a sort of a trampoline system, so the fruit is then rapidly picked when just hooked off the trees, and the trampoline absorbs the shock of the fruit. And then it's covered, and they're all designed to cover the fruit for at least 2 minutes. So we're actually getting beyond that oil phase of the sap, and then it's put into drying. So this is something we could never do this before. We couldn't handle mangoes into bulk bins like this. It would have been a total disaster. These are 400 kilogram bins. So suddenly we're able to mechanize or semi-mechanize our harvesting process, from going from field crates, hand harvesting to semi-mechanized, and the efficiencies within the harvesting system have just, I'll show you some figures shortly, are quite astounding. And on top of that, it's pretty much eliminated sap in the fruit. You don't see almost no sap burn. This system is now moving forward, and it's now moving into robotics. So they're now looking, and the University of Central Queensland has now developed some prototype, and they're out there actually working, doing that, incorporating into those mango harvesters a robotic arms that can actually pick the fruit for them and then put them into the solution. So yeah, so that. I think this is the fourth version of the machine, and they're actually quite happy with it, with its the way it's been able to identify the right fruit and pick. And again, it's another one of those things that helps take labour out of our system. So the results of the addressing the quality issue is that we've pretty much eliminated sap burn in the market floor, in the supermarkets. You don't see much of it. Very rarely do you see it now, as you would before. There are a few other small issues that this mechanisation has created, which we've had to address, which is low level sort of browning of the skins that can have some sap relation. But that process has inadvertently driven the whole the harvesting system change into this semi-mechanised harvesting, and the efficiencies, it was normally costing us around $1.90 to $2.50 a kilo to pick by hand. We're now getting that down to 25 cents to 75 cents a kilo, because it depends on the yield and situation. So it's just phenomenal efficiency gains that's actually started to help us mate, and it's one of the reasons why we now can be somewhat competitive in the export field, whereas before we had no chance of being competitive. It's also resulted in higher retail sales because we're getting much more consistent. The fruit is now consistently landing in those retail stores time and time again with no sap latex burn on it. So what we're looking at now is that as the industry moves into the next era, we have some significant challenges ahead of us. Australia, as you all are probably aware, is a hot country, and the area that I come from is the hottest mango growing district in Australia, in northwestern Australia, and we're seeing some significant changes in the productivity and the trees' response to the environment over the last sort of 10-15 years. So it's happening, and it's starting to impact quite dramatically on certainly in my region and in some of the other regions as well. What we found through some research is when you're getting those, we're getting more and more days with higher vapor pressure deficits. So we're actually physically reducing the tree's photosynthetic capacity because the stomatas close up, as a response to the higher vapor pressure deficit, and photosynthesis rates decline. They actually start making net carbon loss, and we found with the Kensington, even back, which is one of the reasons for its poor performance, we're actually, for 9 months of the year, Kensington was making a net carbon loss. And it was only 3 months a year it was actually able to produce enough reserves. So it didn't have the carbohydrate reserves to even be productive. But also, it's also increasing, with the lack of water flow and the time we get the high vapor pressure deficits, close of stomatas, we're also increasing. Obviously, those days you're getting much higher increase of sunburn. And sunburn, we're finding now, can be 30-40% of the crop can be affected by sunburn. Anything on the western side of the tree, significant losses. So the two technologies that really offer some help, solutions, certainly sort of medium-term solutions, and not necessarily the longer-term solution, genetics and environmental modification around the crop. So we've already looked at some of the genetics and selecting varieties which are more suitable for our conditions. But the other way the industry now is looking at is what we can do by modifying the environment. So part of what I haven't talked about today is we're actually moving into small production, small crops, dwarf fruit stocks, high density, low vigor sort of varieties. But what we're now doing is also combining that with protective canopies. And what we've found is if we can reduce the light levels all we need to do is by 15 to 20%, we're seeing humidity levels raise within that growing area around the crop. We're not seeing, in my area, we used to get photo inhibition where the light was so intense it would be on the other side of the curve and it actually starts suppressing photosynthesis. We now brought it back into the maximum photosynthetic range. And this is having significant impacts on yield. We're seeing increases by 30% of yield. That 30% is primarily because we're not losing 30% with sunburn. So this eliminates the sunburn.
Excuse me, Peter, I'll just interrupt for a few seconds. Can I offer you another 5 minutes? Is that okay?
Yeah, I've just about finished. So
okay,
yep.
Thank you. Yeah.
Second to last slide. So
okay, thank you.
Yeah. Okay. So So yeah, and the quality increases of other things other than sap burners, abrasion, and that we're seeing far less of that. It's actually improving the fruit size and better water use efficiency. So and the upside of it also is we get less bird and bat damage. We have a lot of problems with fruit bats chewing the fruit. The negative side of it is expensive to put in. And you can risk creating a bit of a microenvironment for some of the pests, particularly like mango scale and that, where it becomes a bit softer environment. They tend to like that sort of conditions. So yeah, it's not all positive, but there's definitely moves the industry start looking at this production, start managing the climate change. So I'll just finish up with this slide. It is that one of the reasons why we've had such good sort of uptake and adoption of this technology is at the same point when we changed our research focus to more from production based to sort of market driven value chain approach. We also looked at changing the communication extension, the way it was done. Yeah, historically it was more on output focus. What can you get out? How many farmers can do? At the same time it's changed to more outcome focus. In actually what are the mechanisms to change? What are the drivers of change? And how can we get through to people? So there's been a complete sort of way of thinking of how we deliver our extension and communication project to support these technological changes, and that has been very successful in driving the adoption of the technology. Because as we all know, we all work in the research field. We often have great research that just doesn't get picked up by the industry, and that's the important thing is when something can make a difference is how do we get that adoption. So that's something we looked at quite closely and made some substantial changes in the ability to. So yes, yeah, Jakob. So that's my last slide. I'd like to acknowledge all our collaborators.
Yes. Okay, thank you so much,
Okay, thank you.